Hello, learners. Myself Akanksha, and today I'm here to teach you a topic from Class 12 Chemistry, chapter Solution. As you all can see on the screen, it's Raoult's Law. So let's get into it. Firstly, before getting into Raoult's Law, some important terms that you must understand. First one is volatile substances. Now, what are volatile substances? Gases and chemicals that can evaporate at room temperature to form a vapor. ऐसे gases या chemicals जो room temperature पे evaporate हो जाते हैं. You all must be aware from the nail pinch remover, acetone, rubbing alcohol. All these are volatile substances. Now, the second term is vapor pressure. The pressure exerted by the vapors in equilibrium with the solution or liquid at a particular temperature. जब आपका वॉलेटाइल सब्सटेंस इवेपोरेट हो गया तो उसके वेपर कलेक्ट हो जाते हैं. जब इक्विलिब्रियम मेंटेन हो जाएगा तो वो जो वेपर है वो प्रेशर एक्सर्ट करते हैं ऑन द वॉल्स ऑफ द कंटेनर एंड ऑन द लिक्विड लेयर. So that pressure is known as vapor pressure. Now, the Raoult's law. It was first studied by French chemist F.M. Raoult in 1886. Now, what is the definition of the Raoult law? In a solution, the vapor pressure of a component at a given temperature is equal to the mole fraction of that component in the solution multiplied by the vapor pressure of that component in the pure state. So what Raoult's law says? It says that the vapor pressure of component, जिस भी component का आपको vapor pressure निकालना है किसी भी एक particular temperature पे, वो किसके equal होगा? That will be equal to the mole fraction of that component. You must be aware about from the term mole fraction, which is equal to moles of that component divided by total moles of all the components present in that solution, which is multiplied by the vapor pressure of that component in the pure state. What is pure state? When it is not mixed, when all the components are not mixed. In its pure state, the vapor pressure, that will be known as vapor pressure of that component in the pure state. Now, let us consider a mixture of two completely miscible volatile liquids. Now, what does the term completely miscible volatile liquid means? Completely miscible, that you won't be, when you mix two liquids, and you won't be able to differentiate between the two liquids. That is, there is no formation of separate layer or boundary between the two liquids. Then the solutions will be known as miscible liquids. And what is volatile? That I have already explained before. Now that mole fractions of both the components are given as XA and XB. Suppose at a certain temperature, the partial vapor pressure are PA and PB. And the vapor pressure in pure state are denoted as P0A and P0B. Now, according to Raoult's law, which we have learned from the previous slide, PA, that is the partial pressure of component A, equals to mole fraction multiplied by vapor pressure in its pure state. Similarly goes for PB. Now, from Dalton's law of partial pressure, total pressure will be equal to pressure of A and vapor pressure of B, which is further illustrated as you can see on the screen. Now, you must be aware that sum of all the mole fractions is equals to 1. So, XA can be written as 1 minus XB, or XB can be written as 1 minus XA. Now, as you can see on the screen, this is the curve of the Raoult's law. When XA is equals to 1 and XB is equals to 0, then total pressure will be equal to P0 A. And if XA is 0 and XB is 1, then total pressure will be equal to P0 B. And this is the curve which is shown here. That is for the total pressure, which is equals to PA plus PB. Now, some important points that you must know about the Raoult's law. It is only applicable when two components, they must be volatile liquids and they must form homogeneous mixture. If these two situations or these two requirements are not fulfilled, then Raoult's law cannot be applicable to those liquids. And the liquid pairs that obey the Raoult's law are known as ideal solutions. Although the pairs that are ideal solution are very limited, as you can see some examples on the screen: benzene and toluene, hexane and heptane, chlorobenzene and bromobenzene. Now, the composition of the vapor phase in equilibrium with the solution can be calculated from the partial pressure of the two components. We have all learned about the liquid portions here when the components are in liquid phase. But when the components are in vapor phase, what about their partial pressure? So, the partial pressures in liquid, then the mole fractions in liquid vapor phase here is shown by YA for component A and YB for component B. Now, YA will be equal to, that is the mole fraction of component A in vapor phase will be equal to pressure of component A, vapor pressure of component A divided by total pressure. And for same goes for YB, vapor pressure of B, component B, and total pressure. And this result can be further written as PA equals to YA into total pressure, PB equals to YB into total pressure. Now, this is the NCRT problem which we will be solving using the formulas which we have learned in the previous slides. Vapor pressure of chloroform, that is CHCl3, and dichloromethane, that is CH2Cl2, at 298 Kelvin are 200 mmHg and 415 mmHg respectively. Now what we have to calculate? We have to calculate the vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 gram of dichloromethane at 298 Kelvin. And secondly, we have to calculate the mole fraction of each component in vapor phase. Now I'll show you how to solve this problem by using the formulas which we have learned from the slide. Let's get into it.
Now if we solve this question, then according to question, for first part, mass of CHCl3, given mass of CHCl3 is 25.5 gram and molar mass will be for carbon 12, for hydrogen 1, for Cl 3 into 35.5, which will be equal to 119.5 gram per mole. And secondly, given mass of dichloromethane, that is CH2Cl2, and it is given as 40 gram. Now molar mass, plus 2 into 1 plus 2 into 35.5, which will be equal to 85 gram per mole. Now we have to calculate the moles. Given mass upon molar mass, which will be equal to 0.213 moles. Now moles of dichloromethane, given mass upon molar mass, which will be equal to 0.470 gram per mole. Now for calculating mole fraction, number of moles of chloroform divided by total number of moles, which will be equals to 0.312. And now mole fraction of dichloromethane, moles of dichloromethane divided by total number of moles, and it will be equal to 0.668, or you can also calculate it as 1 minus 0.312, which will be equal to 0.688. I hope this is understood till now. Now we have to calculate P total, and for P total, pressure of chloroform plus vapor pressure of dichloromethane. Now according to Raoult's law, it will be equal to mole fraction of chloroform into my P naught CHCl3 plus mole fraction of CH2Cl2 into CH2Cl2. Now for mole fraction of this 0.312, and partial pressure is given as 200 plus 0.688 into 415, and this combinedly will be equal to 347.9 mm Hg. For the first part, this is the whole solution. Now for the second part, we have to calculate the mole fraction of each component in the vapor phase. So we have calculated, this can be calculated as, which we have calculated in part 1. This is equals to 62.4 mmHg, and for dichloromethane, and it is equals to 285.5 mm Hg. Now in vapor phase, mole fraction is denoted by Y, and which is equals to, as I have mentioned earlier in the lecture, this formula. Now by putting all the values, it is equals to, and for 1 minus 0.18, it is equals to 0.82. So as you can see, easily solved.
As you have seen, this NCRT problem is easily solved from the formulas which we have studied earlier. Thank you. This is for today. Thank you very much.